Hello and welcome. Today we are going to be looking at logistic regression. So if you haven't, I strongly recommend taking a look at the regression and multiple regression video posted before this one. A lot of the basic concepts of what regression is are kind of at least highlighted on that. So we're going to talk about logistic regression, which is a special type of regression. Essentially, we use this tool when the dependent variable we are explaining is dichotomous, a 1 or 0 value. So it only toggles between those two values, and we want to make sure a dependent variable is coded in that way. So today we're going to be using SPSS, Statistical Package for the Social Sciences. We're using version 23. All the commands should be usable backwards into previous versions and hopefully into the future. We're also going to be using the federal sentencing data set for 2006. We're going to be using a subset of 1,000 cases from that entire data set, which we have is about 72,000 cases totally. So we're just using 1,000, a subset of that data set. So logistic regression, as I mentioned, is when we're using a dependent variable that's dichotomous. Today, previously anyway, we examined a total number of months in prison, so we were explaining how many months in prison an individual received. However, today, in order to demonstrate a dichotomous variable, we're going to actually be using probation. So our dependent variable is going to be, did the person go to jail or prison, or were they sentenced to probation, which was essentially coded as 0 months within that. So we've been able to create a dependent dichotomous variable. So essentially we're explaining what factors send someone to jail or prison versus what factors allow someone to walk out without any time in an institution. So as with the previous model, we already talked about running singular models and then running multiple models, or models with multiple independent variables. We're going to hop right to the full model today. So let's go ahead and pull over our dependent variable, which is this probation value, which is really, because one is coded as jail, we're really explaining who goes to prison. The in-out decision, oftentimes what the sentencing literature refers it to as. And we're going to examine a couple different variables here. One is x full SOAR, which is, remember, a metric level variable that is a scale, essentially, of a value of how severe the sentence was. We're also going to add in criminal history, a scale of criminal history, so essentially values within sentencing worksheets as to how extensive their criminal background was. We're also going to bring in a dichotomous race variable, which is 0 for whites and 1 for non-whites, as well as a dichotomous variable for gender, 0 being males, 1 being females. So we bring all those in this covariates box. So these are all of our independent variables. Bring them all in. Our dependent variable is set up here, and let's run the model. Now this looks much different from the multiple regression models that we ran previously. Some of the boxes are intimidating. I'm going to be focusing on a couple different areas of the data to particularly be examining just the key elements of these of this analysis. So going down here, this is going to tell us entirely how many cases were processed. Once again, we're playing with a sample of about 1,000 cases, but only 923 are in the actual analysis. So others were 77 cases were essentially excluded due to having missing data. This is going to tell us the values of our dependent variables. So probation is 0, jail is 1. And then some basic models running everything, kind of trying to estimate essentially the constant, what the model looks like without any variables in it. Now I'm going to hop down to our actual model with all our variables in it. So we're going to look under this block 1 method equal enter. And this is going to tell us essentially we're dealing with 4 variables. Okay. And the first thing I'm going to talk about is the model summary. Now remember, within multiple regression we had a value called R-square and adjusted R-square, and we used the adjusted R-square essentially when we had multiple independent variables, and there were just R-square when we only had one. Now logistic regression, which kind of the underlying, if you will, the engine under the statistical hood here is chi-square analysis, doesn't have a R-square value, and that was the percentage of variation in the dependent variable that's being explained by our independent variables. However, there have been a few different type of attempts to get a similar figure. Two major primary ones that SPSS runs on is the Cox and Snell R-square and the Nagel-Kirky R-square. So these are attempts essentially to statistically measure or try and get close to what that R-square value would be. So you can interpret these once again as the change essentially in this case, probation, in the dependent variable, probation and jail. So the differences between those, the variation, if you will, is measured by this. Once again, it's supposed to be kind of a percentage interpretation, higher, more variance explained. But keep in mind that these both, as we can see, are varying. These are kind of estimates of what that R-square value would be. Typically, in many articles, you would want to report both of these because each one has kind of strengths and limitations depending on the data. So let's go down though to, because what we really want to examine are the variables in our model. Which variables were statistically significant? Which ones were able to explain whether someone went to prison or whether someone went on probation or some other type of deferred sentence? So what we can do is, first thing, we make sure we got all our variables in here. X full SOAR, which is the sentence or the crime severity, criminal history points, the race value as coded dichotomously, and gender coded dichotomously. And we can examine the significance values over here, and we see, lo and behold, everything in this model is statistically significant. Now keep in mind, when we were explaining the number of months with this same sample of 1,000 individuals, okay, that race and gender were both fell to be statistically insignificant. However, in this case, because we're explaining a different dependent variable, whether the person went to prison or not, we find that all of these variables are statistically significant. So how do we interpret this? The coefficients here, because we're essentially, and I don't want to go too far into the math, but essentially we're explaining odds of falling into either probation or prison. Because we're explaining odds, this 0-1 dichotomy, these coefficients aren't as easily interpretable. However, what SPSS does for us is this exponent B value, which is essentially the odds ratio. And this tells us how our odds change, once again, for a 1-point change in our dependent variable. So think of it as your typical odds. A 1-to-1 odd would be just like a 1-to-1 normal, no higher, no more, no less than your typical normal probability. So an exponent B value of 1 indicates to us that at the end of the day, there's no change realistically. So as the exponent B increases, okay, that tells us that the odds of that event happening, in this case a 1 occurring, or us going to prison, or the defendant going to prison rather, increases in value. So the fact that X full SOAR is 1.25 essentially, if we round, tells us that the odds change for a 1-point change in the sentence severity. We get a 0.25 increase in the odds of going to prison. Now keep in mind, this might seem small, however, and keep in mind that's a percentage, so it's about a 25% bump in the odds of going to prison. However, keep in mind that there are multiple categories of X full SOAR that we need to calculate in there. So those odds increase radically when we compound that over all the different levels of X full SOAR. Same thing for criminal history points. We see about a 37% increase for an adjustment in, or an uptick, a 1-point increase in criminal history points. Race, so individuals who are, remember, 0's coded as white, 1's coded as non-white. So a non-white individual, so going from 0 to 1, has an 87% increase in the odds of going to prison. And women, notice how this value, right, from 0 to 1, 1 being the value for women within this sample, this tells us essentially that the increase is, if it's a decimal going lower, then the odds are it's a decrease in that. And what you can do is you can actually grab a calculator. It's easier to interpret when it's on the upper end. It's above 1 because it's directly, the bound is not bound between 0 and 1. So what you can do is you can grab a calculator, enter the value, so you hit 0.369, and then hit to the -1 exponent. This is basically going to give you the reciprocal. In this case, it's 2.71, so this is a 171% increase in the odds of going to prison if you are, or in this case, decrease if you are a female, because the value's under 1. It's a decimal, but it'd be a 170% change in the odds. So this tells us the relative impact of all of these variables. It allows us to compare when an individual has or is of this characteristic. What are the odds? What are the change in the odds of this person, in this case, going to jail? As we see, as the crime severity increases, the odds go up. As your criminal history increases, the odds go up. If you're a non-white defendant, your odds go up. And if you're a female, your odds go down. And these, once again, the odds of 1 in the dependent variable, which is going to prison. Hopefully, once again, this has been kind of a crash course on how to do logistic regression, interpret it. But remember, the fundamental key really comes down to your independent variables, and are they statistically significant? Do they have an impact on the odds of obtaining a 1, or your value, essentially, of success? And the exponent v tells you the magnitude of it. So for a 1 point increase, what are the odds jump? Remember, if it's 1 across the board, it has no impact. If it's above 1 for your exponent v, that increases the odds. If it's below 1, it decreases the odds. And when it's below, to find out exactly what those odds are, take the reciprocal of that value, and that tells you the magnitude. It essentially just changes the math there and makes it a little bit easier to interpret. Hope this has been very helpful in kind of understanding what logistic regression is. And remember, the key is, what is your dependent variable? If you have a metric level dependent variable, okay, that's a variable that is ratio or interval level, you would use regular ordinary least squares, or the, as we demonstrated previously, you would just go ahead and use the linear regression model here. However, if your dependent variable is dichotomous, a 0 or a 1, you would use logistic or binary logistic regression. If you had a ordinal variable, there are other methods, or an ordinal dependent variable, there are other methods such as ordinal regression, which I'm not going to get into in this video, but it functions fairly similarly with some kind of caveats to how logistic regression or binary logistic works. I hope this has been helpful, once again, on a quick crash course. Keep in mind, once again, that we're talking some generalities. I'm using some data that might not be used in a theoretically responsible way, so please do not extrapolate these or generalize these findings to anything in particular. Once again, it's kind of a crash course for demonstration purposes only, and I've just glanced over how logistic regression works, just to allow you to run the models, to get a little bit more comfortable, to kind of understand what's happening. If you are doing analysis that requires extension to policy or things like that, you want to do a little bit more reading and a little bit more consultation on exactly how to code your data, how to run the analysis, and how to interpret. But I hope this has been helpful, alleviates some of the stress about the technique, and helps you along your way. Good luck, have fun, and enjoy your data analysis.